Okay, I hope. Okay, good afternoon, everybody. We'll start with the. Okay, I just see another one again. Hi, Sakya. How are you doing, Sakya? Good. So far, okay with week one, Sakya. Are you there, Sakya? Okay. Okay, in the week one was introductions on the. We give an overview on the transfer phenomena. Transfer phenomena is basically consisting of the momentum, heat, and mass transport. On the week two, we will go into the momentum transport in here. Okay, so the first thing first, we go into the easiest concepts of the momentum transport, which is the Newton's law of viscosity. So as you can see in here, imagine that you put a fluid initially at rest, and then the fluid in here is actually, if you imagine, the top part is actually a very long plate. Okay, you can say a rectangular plate with the length that is much more longer than its width. Okay, and then the same type of plate is put on the bottom. Okay, then at a particular time at t equals 0, suddenly the lower plate is set in the motion. So the motion is set on these directions, on the right directions, with the velocity of v. Okay, we put the symbol in here as a capital V. Okay, so as we set up this velocity, we move the plate, then it has a velocity of v. So it's a constant velocity of v. Then we have a gradual movement in here. Okay, so at small t, the sections of the layers just on top of the bottom one that is moving will start on moving. So this has a transient response. So this will go up again and go up again and go up again until a sufficiently large time where we have a steady state velocity profile. A velocity profile in here will be linear. So the one on the top will be having a velocity of 0, whereas the one on the bottom will have a velocity of v. Okay, so everybody can hear me clearly, right? Can you give a nod, or can you give a sign if you hear me clearly? Okay, good. So this is at large t. So you see that there is a difference in terms of the velocity from the bottom of the plate to the top of the plate. And then as we know in here that we give a definitions that this directions in here is x and the directions on there is y. So there is a velocity gradient in the y direction, okay, and the velocity is moving in the x direction, okay, and this one is called a laminar profile because there is an adjacent layers of fluid that slide past one another in an orderly fashion. Okay, I will not go into these things again. Okay, I mean this. You guys know from the fluid mechanics that there are two types of flow. There is laminar flow and there is a turbulent flow. So in the laminar flow is we have the Reynolds number below 2100, and then that associated with the orderly type of flow. And then the turbulent flow, we have a regular chaotic flow that you see in a high-speed mixer normally. So what are the connections that you can find between the force with the velocity in here? So the connections in here will be the force that is required to move the plate on that x direction, okay, will be proportional to the velocity, okay. It will also be proportional to the area where the force applies. Now the area in here is the area of the plate in here, okay. This force is called a shear force because it's not a normal force. In normal force, meaning that the force is perpendicular to the area where it applies. But in here, the force is parallel to the area where it applies. So that's why it's called a shear force. Okay, there is a difference between a shear force and the normal force. Okay, so based on this postulation of the common sense, then you can see that basically this force divided by the area should be equal to the constant multiplied by the velocity divided by the distance between the plates. Okay, this constant in here is something that we later find out that this one is the viscosity. Okay, and then in here it's very important that you go into your into the notes as I go into the units. You see that how the consistency of the unit. So dimensional analysis is important in here to find out what is the unit for the viscosity in here. Yeah, and you need to make sure that the units in the left hand side is the same with the units on the right hand side. Okay, based on that calculation, then you know that the unit for the viscosity will be equal to Pascal multiplied by second, or something that you call in SI is kilogram per meter second. Okay. Now, these things in here is what we do when we are dealing with the finite entity. If we are dealing with the with something that is you made it into an infinite, or you're dealing with the shell elements, so you go with the differential element basically, then you can change the notations. Okay, F divided by A can be replaced by this tau yx, which is the force in the x directions on a unit area perpendicular to the y directions. Again, this x and y in here has a different direction. So you see, you need to refer to this particular notations in here. So the force in the x direction. Why the force is in x direction? Because you make the plate move in the x direction, right? But the area is basically in the y direction. So the application of the force is in the liquid in the y directions. So that's why this is this can be referred to as tau yx. Okay, this is one way of viewing this particular notations here. Okay, so it is understood that this is the force exerted by the fluid of lesser y on the fluid of greater y. So you see that the fluid of the lesser y has a higher velocity compared to the fluid of greater y. Okay, if I show it in here, then for this particular position, for example, this has a this is what we call as y as lesser y. Okay, and then for example at this particular position, this is a fluid at the greater y. Okay, the transfer is from the lesser y to the greater y. Why? Because this part in here will have a higher velocity than this part in here. This part in here will have a higher velocity than this part in here. Okay, up to this point, I hope everything is clear. Yeah. So in terms of the symbol, then you can convert it into this one, and then it's we want to make it much more specific. So this Vx in here basically define the velocity in the x direction. Okay, and then dy in here refers to the distance between the plates. Okay, to any distance in here. Okay, so any distance in between here. So this is called a dy, an incremental in the y direction position. Okay, this equations in here, equation number 2, which states that the shearing force per unit area is proportional to the negative of the velocity gradient, is often called Newton's law of viscosity. Okay, this equation should not be referred as law actually, because when Newton derived it, it's suggested as an empiricism. Okay, it has been found that the Newtonian fluids can be described by this particular equation. Okay, but not so for the non-Newtonian fluids. So non-Newtonian fluids is something that cannot be described using this equation, and it basically covers something like a polymeric liquid, suspension, paste, slurries, and other complex fluids. Okay, so another interpretation of this equation is that in the neighborhood of moving fluid surface at y equals 0, the fluid acquires a certain amount of x momentum. So the momentum is transferred along this direction. Okay, because a momentum is basically a mass multiplied by the velocity. If you go back to your physics, so there is a transfer of the velocity on this direction. So that means there is a transfer of the momentum in this particular direction. Okay, so that means that this can also be viewed as the flux of the x momentum in the positive y direction, and the flux in here refers to the flow per unit area. When you refer to the flow, meaning that its flow is basically referring to the per time. Okay, and this interpretation is consistent with the molecular picture of momentum transport and also the kinetic theories of gases and liquids. Now, we will not go into the details of this momentum transport and kinetic theories because those belong to the molecular aspects of the problem. So my emphasis on this particular unit is on the microscopic aspect. Okay, so then we can go again and then recap everything else again in here. So momentum goes downhill from a region of high velocity to a region of low velocity. That will be what is important. So the Newton's law of viscosity, or this one, basically, number 2 in here, it can be interpreted as two things. Okay, in terms of the force. So the force meaning it's the mechanical nature of the subject. So in order for you to get that momentum transport, meaning you have to apply a force into your system to make the particular part of your system move. Okay, only with that movement then you have a velocity. Okay, and it can also be interpreted in terms of the momentum transport. So this will have an analogy with the heat and mass transport later on, as we will talk in the week 5 and week 9. Okay, this dual viewpoint will be proof helpful for your physical interpretation. Okay, and then often fluid dynamicists use this symbol called V. Okay, so this one is called a kinematic viscosity. So a kinematic viscosity is different with the normal viscosity, because this kinematic viscosity is actually a normal viscosity divided by the density. It's called a kinematic viscosity. So the unit of the kinematic viscosity will be meter per second square. Okay, on the other hand, for your normal viscosity, the unit will be Pascal multiplied by second or kilogram per meter second. Before I go into the viscosity, then I want to ask you first, when you look at these equations in here, you see that there is a minus sign in here. Anybody can explain to me why we have a minus sign in here? How about who wants to try? How about Jonathan? Why do we have a negative sign in here? Or Evangeline? Yeah, Jonathan.
That's something with direction.
Yes. What about the directions, Jonathan?
The tau maybe acts as an opposite direction force to. I'm not really sure. Yeah, I think it's something with direction only.
Okay. How about Evangeline? What do you think? Why is it negative, Evangeline? Any idea? That's almost there, Jonathan. I will explain it after this, but I want to check. How about Evangeline? You want to try to guess why is it negative? No. Yes, Evangeline? No? Should I just answer it for you? Hello? Not sure. Okay. So I want to ask you, where is the directions that the velocity increase? The directions will be in this direction, right? It will go into the going down direction, correct? So the velocity increase in the going down directions, okay? But the momentum transfer is on the directions where the velocity from the direction of the high velocity to the low velocity. It's the same like the heat transport. So the heat transport basically will transfer from the high temperature to the low temperature. So nature is always fair. So It's not like the economy in the world. So the economy in the world is the other way around. So the richer get richer, the poorer get poorer. Okay, but in here is no. So the velocity will be transferred on the going up direction, but the velocity increase the going down direction. So the directions of the momentum transport is opposite to the directions where the velocity increases. Okay, so this is very important. That it sounds like it's quite trivial, but it's not trivial. So this is something that is very important. So you need to know why you get negative, because when I show you this equation in here, is only show you the concept. I'm talking about the dimensional analysis of the unit and the common sense. But when we go into here, we really go into the details of the system. We look at the case. So this one is negative. Okay, so I hope that you basically understand this point very well. Okay, because as a chemical engineer, this can be overlooked, but you need to know why it is like that. Okay, so in here, in this next slide in here, we are talking about the viscosity. So we are giving a magnitude. So we are referring to several different compounds in here. We are talking about the water, we are talking about the air, we are talking about some of the gases and liquid at atmospheric pressure. So you can see in this table in here, table 1.1.2, for example, the viscosity of water is 1.787, and then the viscosity of air is 0.0001. Okay, so it's very important that you have a feeling of the magnitudes of this of the different things. So the liquid, for example, you know that it has a much higher viscosity than the air. So about 2 or 3 orders of the magnitude higher than the viscosity of the water. So meaning that it resists the movement, okay, much harder than much more than the gas. That's why when you move in air, it's much easier than when you move in the water. Okay, like when you go for swimming, then this basically the resistance will be higher in the water. Okay, then that's the same with these gases again, and then the liquid in here. Okay, and the other thing that is most important thing is, as you can see in here, as you go into the water, the viscosity decreases with increasing temperature. Air, the viscosity increases with increasing temperature. Why is that? So you can go into the bird book and it will be explained that basically because the viscosity decreases with increasing temperature because the momentum transport takes place by intermolecular forces. So as you increase the temperature, the intermolecular forces gets weaker. That's why the viscosity decreases. Okay. Gas, on the other hand, the interaction comes from the collisions between the gas molecules. So at the higher temperature, more collision occurs. So as more collision occurs, then the viscosity increases. Okay, so this is what I called in the beginning, that where a microscopic view of things will benefit from the molecular viewpoint. So a chemical engineer needs to know this kind of magnitude. So you need to have a logic of the viscosity magnitude, okay, and then the dependence with the temperature. That's why I'm putting in this table in here for you to see. Now, we're going to go into something that is more conceptual. So, in the beginning, before we get the Newton law of viscosity, we come with the general form of the Newton's law of viscosity. So, imagine that the velocity in the x direction is a function of x, y, z, and then also the time, and likewise for the y and then for the z as well. So, meaning we assume that because we are dealing with the Cartesian coordinates, so if you go back into your engineering mathematics, you know that we have 3 possible systems. So almost every system that we deal in engineering will be belonging to this particular coordinates. So either can be rectangular coordinates, the cylindrical coordinates, and the spherical coordinates. Okay, and then the way that we describe these cylindrical coordinates and spherical coordinate with respect to the Cartesian coordinates will have their different representations. Okay, it's given in your I think week 2 introductions in here, coordinate system review, for you to refresh this thing again. Then you may ask me why you want to deal with this cylindrical coordinates and spherical coordinates. So for example, if you have a system like a flow through a circular tube or flow through a pipe, it will be easier for you to solve it using a cylindrical coordinates rather than using a Cartesian coordinates. Okay, likewise, if you have a flow surrounding a ball, for example, you have like a ball valve or something like that, and then you want to figure out what is the velocities, or you want to solve that particular problem, then you end up better to use a spherical coordinates. Okay, so you may want to look in here and then refresh a little bit in here. And then I also give something like alonging the volume elements in here that basically connect the. These things will become handy later on as we deal with your momentum transport. So this is something that is very important for you to check again. Now I get back into my week 2 transport again. So let's say we take it like this. Okay, so in such situation there will be 9 stress components. So 9 stress components. So this, the I can be XYZ, the J can be XYZ. So you have 3 times 3 multiplied, that means 9. Okay. So this one is showing you the possible forces that are acting on the planes in the fluid perpendicular to the 3 coordinate direction. So this one is on the force in the X direction, this one is on the Y direction, and this one is on the Z direction. Okay. I think this one is continuing the generalization of internal viscosity. So let's say we put in the center of the volume element at the position of X, Y, and then Z, and then we scrap half of the cube, and then we want to know what will be the force needed to replace that half of the cube that we have removed previously. Okay, so in here, this particular force in here is something that associated with the pressure forces, and then this one in here is something that we associated with the viscous forces or the shear stress. The pressure is always perpendicular to the area where it applies. Okay, as you can see in here, is always normal to that particular area, but the viscous force is not. It can come at a little bit, and it makes an angle with the pressure. Okay, so this thing is something that you need to understand, because this will come into your momentum transport utilization later on. So the pressure force is always perpendicular to the exposed surface. That's why it's multiplied by the unit factor called this one in here. Okay, this one has always a perpendicular directions to the exposed surface. Okay, and then that's the same with the Y and then with the Z. So this pressure force is exerted when the fluid is stationary as well when it is in motion. Okay, the viscous force, on the other hand, it only plays when there are velocity gradients within the fluid. So if there is no velocity gradient within the fluid, then there will be no viscous forces because of this particular term in the equations. Okay, so that is something that is associated with the pressure, with the viscous force. Okay, in figure 2a we see a force per unit area called tau x, and then tau y, and then tau z. Okay, then we can break it down into tau xx, tau xy, and tau xz, because this is particularly this unit in here can be represented in terms of the tau x in x direction, tau x in y direction, and tau z in the z direction. Okay, so this one is basically can be broken down into the respective components in the different coordinates, right? And if you break it down like that, then you will have something like this. Then you can see that pressure only applies when you have the first subscript equal with the second subscript. In here as well, pressure only come out when this y is equal to this y, and then when this z equal z. The pressure is always absent on the other the other formula that has a different subscript. Everybody get it up to this point. Huh? This looks subtle what I'm telling you, but I just need to tell this to make you sure that everything is clear rather than you get a confusion later on. Okay, you can break it down like this basically, and these are what we call the molecular stress tensor. Okay, this tabulation is basically a summary of the forces that includes the pressure and the viscous stresses. And if you want to talk about the details of this, then you can put it in here. So it can be split into the normal stresses and the shear stress. The pressure is always coming up on your normal stress. Okay, and the pressure is always absent on your shear stress. The quantity in here is called the Kronecker delta. Like I tell you before in the last week, because we have a 2 directions quantity in here, then this is called a tensor. Okay, this is called a tensor because it has a 2 direction. Okay, so for example, in his particular force, the force in the y directions or the momentum in the y direction is transferred in the x direction. Okay, so unlike momentum or unlike velocity, then this particular force, okay, it is a tensor quantity, right? And then we can define that the viscous stress tensor is something that we put as a tau, and then the molecular stress tensor is something that we call a pi. We give a pi. Okay. When there is no chance of for confusion, the modifiers viscous and molecular may be omitted. Now, we go into how these generalizations can be simplified now. See, if you have these viscous stresses, meaning you may have several different combinations of your viscosity. So in I direction you have 3, in J you have 3, K you have 3, L you have 3. So 3 times 3 times 3 times 3 will be 81. So this is not something that is possible to be solved because it is quite complex and involving too many variables. But we can make simplification. So for example, we assert that the time derivative or time integral will not appear in the expression. And this is valid if your fluid is just a simple fluid, it's not a viscoelastic fluid. Okay? And then we can think again that if there will be no viscous forces present if the fluid is in a state of the pure rotation. That means that this tau ij should be a symmetric combination of the velocity gradient to fulfill the conditions that there will be no viscous force if the fluid is in a state of pure rotation. That means that the only possible combinations of the velocity gradients within the equation should be this one or this one, or this one plus this one. Okay, so by doing that thing, then we can come into the conclusions that your shear stress should be represented by equations shown in here, in equation 6 in here. So in doing these things, we have reduced the number of the viscosity coefficients from 81 to 2. But in reality, actually, this takes many decades for us to go into these conclusions in here. Now, we take that this A in here equal to B to the viscosity because this is similar with the Newton's law of viscosity that we described earlier. Okay, and then the B in here is taken to be equal to 2/3 of the mu of the viscosity minus the dilatational viscosity. Okay, so from our study in the molecular level, we know that from the kinetic theory that K is equal to 0 for the monatomic gases at low density. Okay, so then with these things in here, we can simplify the steps to become equation 7. Okay, I hope everybody understand up to this point. Yeah, I keep on continuing. Now, this equation 7 in here, or this particular notations in here, can be changed into vector tensor notation as shown in this equation 8 in here. Okay, this will be the equations that we are dealing in all the situations for the momentum transport. Okay, these equations in here is is basically used in all the problems, including your assignment 1 as well, to do these things. Now, in equation 8, there are important quantities in here. So something that we call a mu in here, and then this k in here. Okay, this is a properties of your particular system. So if your system is a liquid, then this is a property of the liquid. If your system is a gas, then that's property of the gas in here. In solving the fluid dynamics problem, it's generally not necessary to know this quantity of the K. Okay, if the fluid is a gas, then this K can be assumed to be equal to 0. If your fluid is a liquid, it becomes incompressible. When you mean something that is compressible, meaning that if you change the pressure, then the density will change. If for a liquid, normally if you change the pressure, then the density does not change much. Okay, so it's called incompressible. So this term for incompressible liquid fluid, then this term in here, this diff F, this diff V, it can be regarded as 0. Okay, the only case where dilatational viscosity K is important is when you are dealing with the sound absorption in polyatomic gases or the fluid dynamics of liquid containing gas bubbles. Now, this term in here in equation 8 is something that can be broken down into their respective components or tensors. Okay, so if you are dealing with the Cartesian coordinates, you have to use this particular table. Okay, this particular table, and this particular table is for the cylindrical coordinates, and then this particular table is for the spherical coordinates. Where you get this one is something that you go over here. So you go into the appendix. This is appendix A, is talking about the vector and tensor notation. So this also explains how you convert the vector representations from the Cartesian coordinates to the cylindrical coordinates and spherical coordinates. It is not something that you really want to deal if you are still a beginner, but if you have extra time and you want to try your mathematical skills in the vector and tensor conversion, then you can go into the appendix A. In most cases, in what we are doing in the basic tensor phenomena, we will deal with this appendix B, so Newton's law of viscosity. So you can see that I just copy and paste this table in here into my slides, and then this one is for the cylindrical coordinates, and then this is for the spherical coordinates. We have the same as well for the Fourier's law of weak conduction, but it's much more simplified because these are not the tensor quantity. These are just a vector quantity. Okay, so that's what I'm telling, that the momentum transport will be a bit more challenging. But if you can deal with the momentum transport, then the heat transport should be easy for you. Okay, so we have done the molecular momentum transport. So up to this point, any questions before I continue into the next subject of the convective momentum transport? Any questions from everybody? Evangeline, Tiara, Daniel, Sakya, Alvin, Jonathan, Stephanie, everything clear up to this point? Good, huh? Am I being too fast? Or is it good up to this point? No? Anything that you want me to go back and explain? Hi, Gladys. How are you doing? Good. Jonathan, is it okay? Explanation, is it fast, or do you want me to go back to any particular things before I keep on going? Because this is a bit in the afternoon, so probably somebody will feel sleepy, and I think my pace sometimes can be quite quick, so I need to stop and then ask you guys first before I keep on continuing. Okay, all good, I'll continue. Now, we have deal with the molecular momentum transport. So molecular momentum transport is the mechanisms, is the basic mechanisms that we deal when we have a difference in terms of the velocity. So the velocity gradient is there. So it's not the only contributors to the momentum transport. We have another significant contributor to the momentum transport. It's called the convective momentum transport. So convective momentum transport occurs when there is a bulk flow of movement of fluid. Okay, so if you have a density movement, density associated movement, or there is a clear movement of one bulk fluid of body from one positions into the other positions. Okay, like when you pump your fluid, basically, then you have a convective transport. Okay, in here we have the same diagram that we use for the molecular momentum transport. Okay, except this time we are dealing with the bulk flow of the fluid. So let's assume that we remove half of this cube, and then we want to find out what are the forces that are needed to replace that half of the tube in here, in this particular area, in this particular point in here. Okay, so and then if we go and look in here, we know that the fluid carries with it a momentum rho v per unit volume. So along the x direction, the momentum flux will be velocity along the x directions multiplied by the rho multiplied by the v. So, or what you can imagine in here is your velocity in the x direction multiplied by this momentum rho v per unit volume. Okay, so you can go and then check what is the unit for this one to make sure that the derivation is correct. Okay, you have three types of forces in here. So the forces in the x direction is this rho vxv, in the y direction is rho vyv, in the z direction is rho vzv. Okay, and each of these vector also has an x, y, and z component. Okay, so at the end of the derivations, what you can see in here is that if you break down all these convective momentum components, okay, on this particular direction 1, 2, and 3, then you can have this table in here. So for the directions normal to the x, you have three different vectors, and the same with the y, you have three different vectors, and then z you have three different vectors. And then this one is called a convective momentum flux tensor. So the thing that are different with the molecular momentum flux in here is the quantity, the term rho in here. The term rho in here is the density. So when there is a movement of the bulk part of your fluid, then you have, for example, this rho in here. Okay. Now I don't want to go through the details in here. This is just a concept in here. You can read this thing yourself. Now we can sum up the combined momentum transport. Okay, so we have talked about the molecular momentum transport. Molecular momentum transport in here is represented by this term called pi in here. Okay, the convective momentum is represented by this term called rho v multiplied by v. Okay, the molecular contribution term in here consists of two different contribution. So one is the pressure and one is the shear force in here. So you can break it down from this particular, this is called a combined momentum flux. It's into two contributions, and then since the molecular momentum flux has two contributors, so it becomes three terms in here. Okay, now remember that the pressure is only coming up when the direction is perpendicular to the exposed surface. So if you go back into your slides number, where is this one? Slide number 14. Remember this term, perpendicular to the exposed surface. Okay, so you see also in here that the pressure is always perpendicular to the particular surface that we are inspecting, right? And that has a consequences into these things in here. So as you can see that pressure is only coming out when the two subscripts are equal in here and in here. So that will be reflected in the final term for your combined momentum flux, right? So it will be combined in here. So if, for example, if we are talking about the xx, then the pi xx in here will contain two terms, pressure and the tau xx. Okay, On the other hand, the pressure term will not appear in this term called the xy. Okay, I think everything is very important that you understand this point. Hi Sarina, I hope all is good with you. Then we come back again into the definitions of these terms. Again, pi xy refers to the combined flux of y momentum across a surface perpendicular to the x direction by molecular and convective mechanisms. So the directions of the momentum is referring to the second subscript. The directions of the momentum transferred refers to the first subscript. Okay, everybody get it up to this point? So let me go back into. I need to go very slowly in here, because those that that does not digest this thing is very this is very important, because otherwise it will be confusing later on. Okay, so the second index in here gives the component of momentum being transported, while the first index gives the direction of the transport. So if I go back into my which one is it? The very first picture in here. So the velocity is in the x direction. So the momentum is in the x direction. Okay, but the momentum is transported in the y direction. Why we call it a momentum transport in the y direction? Because the velocity in here is imparted to the velocity in here, and the velocity in here is imparted to the velocity in here. What makes the velocity at this particular layer is because the bottom layer is moving. Okay, so that's why the momentum transport is in the y direction. So if I go back into this particular formula, this x in here refers to the directions of the momentum, or the direction of the velocity. The first subscript in here refers to the directions of the momentum transport. Okay, did everybody clear up to this point? Because if you don't get clear up to this point, then it will be very difficult later on for me to go into the example, and you will get confused later on. I just want to make sure that everybody is clear for this particular point first. Okay, Gladys, you understand for this particular point? Okay, that's the notation that the notation that is very important. So this second subscript in here indicates the direction of the momentum. The y directions in here refers to the directions of the momentum transport. So if I change these directions into z, and then these directions into x, then the momentum will be on the z direction. Okay, but the directions of the momentum transport is in the x direction. So this can change whatever we want. We can always change this thing. Okay, I mean we can replace this x with z. We can replace this x with y, for example, and then we can replace this y with x, or we can replace this y with z. So it's very important that you know that the convention is there, even though we change the things. Okay, so it's applicable for the molecular momentum, and it's applicable for the convective momentum flux, and it's also applicable for the combined momentum flux. Okay, so the table 1.7.2 in here is giving you the convective momentum flux tensor, the viscous momentum flux tensor, the molecular momentum flux tensor, and the combined momentum flux tensor. Okay. Now, based on everything that we have shown earlier, it looks abstract for you at this particular time, because you have not really applied that thing into the real situations, right? I mean, you just have all the notations, and you don't know actually how to apply that thing, but it will become clear when we discuss the example. So I think this week I want to go a bit faster so that you can start with your assignment 1. because that assignment 1 is something that is quite complex. So I will go into your week 3 again, just to continue, and then let's go into the first example a little bit until I would say past 2. Everybody has had their lunch ready, yeah, I hope. Or you want to get a 5-minute break? Who wants to get a 5-minute break before I continue again to the week 3? Everybody okay if I continue and just finish it by 2:30, for example? Okay, yeah? I continue. Okay, so week 3. So all those concepts that we have described just now, we want to show how to apply those concepts to obtain the velocity profiles for the laminar flow of fluid in simple flow system. For the momentum transport in here, we will give you 4 simple systems to follow first to show a gradual increase in the concepts. So the role of the pressure and the viscous forces and the gravity forces, and then the applications into the different coordinates. For example, the Cartesian coordinates, the circular, the cylindrical coordinates, and the spherical coordinates. So this is not like the introductions where we use macroscopic balance, but this one is, we are going into the microscopic level. So we will have a velocity profile, okay? And then once we get the velocity profile, we will be able to determine the maximum velocity, the average velocity, or the shear stress at the surface, okay? The methods and the problems that we will show in these 3 weeks for the momentum transport is related to the simple system called a steady rectilinear flow. So something that is meaning by the steady rectilinear flow is that the pressure, density, and the velocity components at each point in the stream do not change with time. Okay, and these are just giving you a bit of illustration into the difference between the laminar and the turbulent flow. So laminar flow is shown by A in here. The turbulent flow is something that is much more mixed. So if I'm in my previous week, we deal with this one in the second example of the different levels of the modeling, when we are talking about the cooling of fluid flowing in the pipe. Okay, so when we are dealing with the shell momentum balance, then equation number 1 is our most important equations. Okay, we need to focus into the shell element of the fluid, and depending on our postulations, we will be able to set up this rate of momentum in by convective transport. So whatever goes in will go out, and then we need to also account for the force of the gravity acting on the system. So this is a rather restricted statement of the conservation of the momentum. Okay, and then this one the expression for the convective momentum fluxes will be given in the table 171, and then the molecular momentum fluxes is given in the table 1.2.1. So something that you want to go and look into this one again. This is giving you 171, okay, and then you go back again for your molecular momentum flux. That one is represented by table 1.2.1. Okay, so this is interrelated from the week 3 to week 2, right? And then remember that the molecular momentum flux include both the pressure and the viscous contributions. Now, in here we give you the procedures for setting up and solving the viscous flow problem. So the first, identify the non-vanishing velocity components and the spatial variable on which it depends, right? And then we use the equation 1 to write the momentum balance over a thin shell perpendicular to the relevant spatial variable. And then, as I show you in the previous example, then we let the thickness of the shell approach 0, and then we use the definition of the first derivative to obtain the corresponding differential equation for the momentum flux. Once we integrate, we will have the momentum flux distribution, and then we insert the Newton's law of viscosity to obtain the differential equation for the velocity. This one can be integrated to get the velocity distribution. Once we get the velocity distribution, then we can get the other quantities such as the maximum velocity, average velocity, or the force on solid surfaces. Okay. Now, transport phenomena is a rather mathematical subject, but what is important in the transport phenomena is the physical significance. And when we have that mathematical derivation, it has to always be connected with the statement of the velocity or stress at the boundaries of the system. So the three most common conditions for the momentum transport is at the solid fluid interfaces, the fluid velocity will be equal to the velocity at which the solid surface is moving. So if your solid surface is not moving, that means that velocity of the liquid directly exposed to that solid surface will be 0. Okay, so that is something that we call a no slip condition. Okay, and then at the liquid interfacial plane of constant x, basically the velocity and the stress tensor will be continuous. So then you will ask me why at what condition that you have this liquid. So for example, if you have a two immiscible liquid phase, for example, you know oil and water does not mix, right? So in extraction system, for example, you may have a flow of two different liquids that does not soluble with each other. So these things will be applicable to that particular system. Okay, and then the last conditions in here is the conditions between liquid and the gas. So at the liquid and gas interface, the stress can be taken as 0. And at the liquid gas interface plane of constant x, the stress tensor can be taken to be 0. This is because we take this assumption is because we know that the gas side velocity gradient will not be too large. And this is reasonable because the viscosities of the gases are much less than those of the liquids, as what we have shown in the table in the week 2 before. Okay, so now it's very important that we are only dealing with the simple conditions that and in the simple condition that we assume that there is no material passing through the interface. So there is no absorption, dissolution, evaporation, melting, or chemical reaction at the surface between the two phases. So what we are giving in here, the example is a very simplified situation. So it's only showing you that the system is basically does not consider the heat transport or the mass transport at all. So now let's go into the first example in here, the flow of the falling film. So imagine we have this kind of flow where the flow is quite slow, not very fast. Okay, there is a liquid film that is flowing, and then the flow in here is laminar. Okay, and then we are interested at the region to check the velocity profile from between this region to this region in here. And then in this particular example, we want to show you the role of the pressures and of the gravity forces. Okay, and then also how we use the Cartesian coordinate to show this particular to show this particular problem. Okay, I will not go using this one, but I will rather go using my paper that has been solved in here. Okay, I think this one is also given in your canvas in here. Okay, you can check that this one is given in week 3. I think you have to go into the week 3 example because we are going a little bit more so that you can start with okay, I cannot go with the dashboard. Now I go back again basically. Okay, I go back again. So let me go back into the next one. Anyway, I give it in the week 3. You guys can go and have a look at this particular point. I just want to go into the sample much more detail. Now, the flow of liquid down an inclined flat plate of length L and width W. So we make a mental picture that our systems is basically consisting from this from here. So the length is from this to here, the length is L. And then when we take a 3D image of the picture, we can visualize that we have a width of W. And then from the bottom to the top, it's basically the film has a thickness of this thickness. You see, these things, I think we call it as a theta. I think if I'm not wrong, okay, as the thickness of theta. Now we take the assumption first. The viscosity and density of the fluid are constant, so we don't care about the variations of these two properties. The disturbances at the edge of the system at z equals 0. So at z equals 0 is basically at this particular position, at this particular position. At z equal L at this particular position. At y equals 0, y equals 0 now. Not that you are taking the position of the 0, 0, 0 coordinate, or the initial coordinates of 0, 0 is from this position in here. Okay, so or if you take it from this particular term, is you take it at this particular position. It's very important where you take the 0, 0, 0 coordinates position in here. So you take it in here, then you see that whatever at the end can be neglected. So the disturbance at the edge of the systems can be neglected, and this will be valid if your W and L are much larger compared to the film thickness theta. Okay, so that thing is very important. And then at small flow rates, the viscous forces prevent the continued acceleration of the liquid down the wall, so that we can assume that the velocity direction is independent of z. If you see this particular picture in here, it's become clear that you only have the velocity going down this direction in here. Okay, that the velocity is in the z direction, and we want to assume that we don't have the accelerations in the z direction. Okay, or otherwise our solutions will not be a simple solution, but it will be a complex solution. Now we go with a very important step now. The postulation in here will give us the solutions for everything. The postulation in here is in terms of the velocity of in the z direction, the velocity in the x direction, and the velocity in the y direction, and also the pressure force. Okay, the pressure force. So as we can see in here, we have the three directions. You can make a mental picture of your system. At the particular point, we only know that the flow is going down to this direction. So meaning we have a velocity in the z direction, right? And then the velocity in the x direction will be 0 because the liquid does not flow to the bottom. So it does not flow to this direction. And the velocity also does not flow in the y direction. So that's why we can simply say that the v in the x direction is 0. V in the y direction is 0. Okay. And then the pressure is a function of the x. The x meaning the functions of this in the bottom direction. Why? Because the pressure is often a function of the depth of the liquid. Okay. So we will assume that the pressure at these particular positions will be different with the pressure at the, let's say, at the bottom. Okay, because the pressure is normally a function of the liquid depth. So this is something that is rational basically. And then we can also assume that the velocity in the z direction is a function of the x. So why is it a function of the x? Because the velocity on the top will be different at the from the velocity at the bottom. Because the velocity at the bottom is basically equal to the velocity of your solid surface, and we know that the velocity of the solid surface is basically 0 because this plate does not move. Okay, so by the common sense, we know that the velocity on the top should be much faster than the velocity on the bottom, because there will be basically the contact with the solid surface in here will prevent the solid to move. Okay, so by rational thinking, we know that the velocity in the z direction will be a function of x. Okay, up to this point, I hope everything is clear. Okay, so these things will determine our next step, right? Then let's make, when we are making this shell element. So the shell element is basically we make a cut on the x direction. So we take a thickness of delta x, and that thickness of the delta x, or if I show you in this particular these things in here, this particular thing in here, if we make in a thickness of delta x in here, okay, something that we take, if so this we take the shell thickness of this with the delta x in here. So we are taking that shell elements in that particular delta x. Why we are taking a shell element with the thickness of delta x? Why is that? Because we assume that the velocity changes in the x direction. That's why the properties will vary in the x direction. That's why the shell element is taken with the thickness of the delta x. But the length and the width is the same with our system. Okay, I hope everybody hear it clearly. So the postulation in here is very important, because this will connect with your velocity profile, and then with the subsequent steps in your system. Okay, so once we draw our shell elements in more detail, we know like this, right? And then we can draw where the respective flux or the respective force is working. So we have this xz, yz, zz. Okay, so we can inspect the z momentum balance over the shell. So the rate of the z momentum in a cross surface at y equal 0. So at this particular position at y equals 0 in here, the surface area where basically the force applies is represented by the L multiplied by the delta x. So that will be this particular area in here. Okay, and then multiplied by this combined momentum flux in yz. Okay, at y equal 0. So I'm talking about the surface in here. So that will be inspected at y equals 0. Okay, and then we can then connect this tau yz in here with your postulations in here. Okay, so if we go into the table that we showed earlier in here, the table in this particular things in here, we are using, remember that we are using a Cartesian coordinate. So that tau yz in here is given by this equation B15 in here, right? By this B15 in here. Now, this Vz in here, del Vz per del y is equal to 0. Why? Because our Vz in here is not a function of y. So when it's not a function of y, that means if we derive with respect to y, it becomes a constant. When you derive when you differentiate the constant, it becomes 0. Okay, and then this Vy in here is 0. Okay, so just don't look at this. This one is wrong statement. Okay, so this Vy in here is 0. So the derivative of 0 will be 0 basically. Okay, so the tau yz in here will be equal to 0. The second term in here also will be 0, because even though the rho exists, or this Vz actually exists, then because Vy is 0, then this will become 0 because it's multiplied by 0. So this term will be 0. This term will be 0. Okay. Then we inspect the other. We have inspected this the force along this particular surface already. Let me check this one. Right. We check this surface in here. We check this surface. So in this rectangular unit, we have 6 surfaces. So we have to inspect the other 4 forces. Okay. Now we are talking about the rate of z momentum in a cross surface at z equal 0. So where is the location where z equal 0? So the location at where z equals 0 is at particular locations in here. So the area where it applies is equal to the W multiplied by the delta x. And then we multiply that with the ZZ. At ZZ is this one, this particular force. And then we need to inspect that one is at Z equal 0. So that one is W delta x multiplied by the pressure plus tau ZZ plus pro VZ at Z equals 0. Okay, at this moment we don't want to infer. We don't want to go into the details of the components. We go with this later. Okay, let's go with the other one at this particular ends. Okay, so we inspect this one is W multiplied by delta X multiplied by this rho tau ZZ plus pro VZ. Okay, so then after these two, then the remaining one that we have to deal is with this one from the top and the bottom. So that one will be multiplied. The force will be multiplied by this particular rectangular area L multiplied by W, and then when we break down, when we convolute the breakdown into the contributors, then we will get this one, and then with this one. Now we can go and inspect this one. This tau at ZX, tau XZ is something that is explained with this one here, right? This tau XZ and XZ. So you need to go back into the postulation and then check what is this. So this particular term will be 0 because your Vx is equal 0. And this term in here exists because your Vz is a function of x. So you cannot, this term in here is present. Okay, so then the last term that we need to inspect is the gravity force. So the gravity force acting on fluid in the z directions. Note that the gravity force is going into the bottom, right? It's always going into the bottom. So we want to know what are the contributions in the direction of z. So let's imagine we have this rho g and then we have this fg. So we are interested to find out the quantity of the fg. So if we make, if there is an angle of beta between the plate between the flow directions with the gravity directions, then we can simply take that this Fg in here is equal to rho g multiplied by the cos beta. Okay. Then following our momentum balances in there, we go and then we plug in all this quantity into that particular momentum balance. So this is what we show you in this particular slides. Okay, so we show you this particular slides in here. We use this string here. Okay, once we know all the work, once we figure out everything, then we put out this into this term in here. Okay, then now we deal with the simplifications. So we have not figured out what is this tau ZZ. Go back into your cylindrical coordinates and then you go into these equations, put it in, this tau ZZ in here. You see that the second term in here will become 0 because we are dealing with the incompressible liquid. Because this is just simply a flow of a liquid down an inclined flat plate of length L and width W. Right? So this one will be equal to 0. So you only need to deal with this one. And this term in here will be equal to 0 because your velocity in the z direction is not a function of z. If it is a function of z, meaning that it can slow down with increasing z, or it can become faster with increasing z, and we don't, like what we said already in front in here. Our assumption is that basically the small flow rates viscous forces present the continued acceleration. Okay, so the Vz is independent of z in a short distance down the plate. Okay, so then this one can be shown. I showed already that this one becomes 0. So that this meaning that this one is 0, this one is 0, and then now you also know that the Vx is equal to 0 because there is no flow in the x direction. And then now the pressure is only a function of x. So the pressure at z equals 0 should be the same as the pressure at z equal L. And we can take these two as P. Okay? So that means if we plug in this P value in here, so you just substitute this P at z equals 0 as P, and then you substitute P at z equal L as P, and then also notice that the Vz is not a function of z. Okay, so this this Vz at z equals 0 will be equal to z at equal Vz at z equal L. So as a result, once you plug them in, then they cancel each other. So at the end of the steps, you only have this one. Okay, and then this one is equal to this one in here, right? Then you go up again, you go here, and then you end up with this particular equations in here, and then you can divide L multiplied by W by delta X, then you get this one. As you take the limit to delta X approaching 0, then you will get this the derivative of your shear stress xz over x is equal to rho g cos beta. So again, I want to test you again in here. So this z in here, so what is the velocity of, what is the direction of your momentum? Sarina, can you tell me what is the direction of your momentum in here? Are you still there, Sarina? Or Jonathan, what is the direction of your momentum in here? And what is the directions of your momentum transport in here? Jonathan, are you still there? Or probably Alvin? What is the direction of your momentum for this equation? For this one. And what is the direction of your momentum transport? The second subscript in here represents the direction of your momentum. Okay? Yep, correct, Sarina. The directions of your momentum transport is the first subscript, so it's x. So the momentum transport basically is transferred along this x direction, okay? But your momentum transport is on the z. Your momentum is on the z direction because the velocity is in the z direction, but your momentum transport is in this x direction. So this is consistent with the picture of your system, right? So that is very important. Then now you integrate. As you integrate, this is a simple integration. Then you have this constant. Now, how did you get your value of your constant? So you notice that in your system in here, we can simply use our first boundary conditions in here. Where's the first boundary condition? So the first boundary conditions is something that we put in here. I think this one. At the solid fluid interfaces. So we are referring to the first condition. So that we have two different boundary conditions. On top in here, our liquid is in contact with the atmosphere. So that the one is in contact with the gas or air atmosphere. On the bottom in here, the liquid is in contact with the solid surface in here. Okay, so if we are using the boundary conditions that we will use later on for our velocity, then we have to use the conditions where the velocity is 0. At the top in here, we can use the conditions where basically the shear stress of the liquid will be 0, because we have discussed that the viscosity of the gas is negligible compared to the viscosity of the liquid, right? That is what we discussed before already. So now we are just applying the one on the top. So the positions on the top is represented by the coordinate at x equal 0. Remember, we inspect again the coordinate in here. So the position at x equals 0 is the area on top in here. Okay, that particular area on top in here is where the liquid is in contact with the air atmosphere. Okay, so meaning that we can simply define that your shear stress is 0 at this particular position. So this gives you the constant of 0. So your tau xz is a linear functions of the in the form of the rho g cos beta x. So at position of x equals 0, or on the top in here, your shear stress will be 0. At the bottom in here, your shear stress will be rho g cos beta multiplied by the thickness of your film, this one, theta. Okay, so that's what we can infer. So as what we can draw later on in this particular position in here, right? This is what we draw in here in the momentum flux distribution. As you can see that this has a linear distributions. Okay, and then we can go on again. I think I will just go on with the velocity distribution, and then I will stop it here because we have gone into quite intensive 90 minutes of the lecture. I have to do this because of the accreditation, so I lose my time yesterday, right? Once we get this tau xz, then we can plug in your Newton's law of viscosity, right? As we infer from the top, this tau xz is equal minus mu dvz over dx. So you substitute this one, and you get these equations in here, right? Once you get this equation in here, then you can integrate in here. You integrate, then you have another constant called C2. Then, like what I told you again, there is a boundary conditions on the bottom of your liquid in the bottom, where it basically in contact with the solid. So that at a particular position, that one we have a no slip condition, where Vz is equal to 0. So let's substitute that thing into here. So we substitute 0, and then we plug this theta into this x. Okay, then we can get the value of the C2. So your boundary condition is essentially to get the value of the constant in your ordinary differential equation to make it match with the physical situations. So once you integrate that thing, then you will get the parabolic velocity profile for your velocity distribution, right? So your velocity distribution will have the form of like this. So in the bottom it will be 0, then it will go and vary parabolically, okay, up to the top. So the maximum velocity will be the one on the top in here, okay. So in the beginning you don't have this particular picture. You don't have the picture of your velocity distribution in your system. You also don't have a picture of your shear stress in your system. So with this microscopic view and the postulation that you make into your system, accompanied with the shell momentum balance and all the concept that we have given, you are able to get more details into your system. Okay, and this can be very important later on as you deal with the average velocity, or you deal with the other. We will deal with the Hagen-Poiseuille equation. So, for example, Hagen-Poiseuille equation is derived from this microscopic point of view, for example, or in the heat transfer, you can figure out your temperature profile, and then you can find out, for example, the efficiency factor and the other things that will be very important for your design of your unit operations. Okay, up to this point, I think I will not continue further. I hope everything is clear. I think I have tried to load you with quite many informations, but also with the explanations. And is there any questions that you want to ask up to this point? Evangeline, any questions? No? Tiara, any questions? Evangeline, are you there? Okay. Daniel, any questions? Everything so far so okay? You can ask anything up to this point? No? Daniel, you something, okay. Sakya, understand? I mean, is it okay? Any questions? Gladys? Sarina? Stephanie? Jonathan, Alvin. Okay, with that thing, everybody, next week I will discuss flow through a circular tube, and then I will go into the average velocity, and then I will go more into the details. But our drop-in sessions will get shorter each time because I'm a type who does not like to fit in as many, because saturation will not work good for your brain. But rather, what I want from you guys is basically I go a bit into the details in the beginning. You come back to me, tell me which part need reinforcement. So which part that is not clear, which part you need more explanation, then we can use our drop-in sessions to explore those things and make it much more better for you. Okay, that will work well, more than I fit in much more thing into your brain. Okay, so if you can go into these particular things and then watch the next example, then you will be ready to start working on your assignment 1. And I would suggest everybody to start working on that thing, and then ask if you have any difficulties. I will provide you a hint, but I will not do your assignment for you because it has a 25%. And I'm always contactable, but sometimes it may be I will respond a little bit slow because I have something else to do. And I hope so far, if everything is good, then we will just conclude the sessions in here. Then we see you again, I think, next week's session. I think probably I'll try to make it into a smaller chunk on Wednesday, and then also another smaller chunk on Thursday. That will be much better than I give it in one go like this. But because I have to do it this week because I have the accreditation, so I have to cancel my session yesterday. Okay. Thank you everybody for coming. I will stop my recording.